let's take a look at finding area horizontally. For instance, let's take a look at this region that's bound by the parabola f of y equals 12 minus y squared and the y-axis. Now normally we look at this as a vertical sort of area. By that I mean we use a vertical representative rectangle like this, which means that the base of our rectangle, because it's a horizontal distance, would be the change in x. That means when we find the height of our rectangle, this height right here, we have to do that in terms of x. The problem with that is that our function isn't written that way. It's written in terms of y. F of y equals 12 minus y squared means x equals 12 minus y squared. Now we can rearrange this. It's not that bad. We can add y squared to both sides and subtract x from both sides. Then get y alone by taking the square root. Now remember, when we take the square root of that, we're left with plus or minus the square root of 12 minus x. The reason we have plus or minus is that the top of the curve is going to be y equals the positive square root of 12 minus x, and the bottom of the curve would be the negative square root of 12 minus x. Okay, well now we're ready to find the height of that rectangle by taking the big curve minus the small curve, the big curve being the positive square root, and we're going to subtract off the little curve, the negative square root, and what we're left with is 2 square root 12 minus x. So we set up our definite integral, and it's going to be that 2 square root of 12 minus x dx. The interval goes from 0 all the way out here to 12. The ends of our boundary, the ends of our interval in terms of x. Now this integral looks innocent enough. However, because we have a function inside of that square root, that means we're going to have to use u substitution. So u is 12 minus x, which would mean du is negative 1 dx. So dx is negative 1 du. Next, we got to come over here and substitute. So that 12 minus x is our u, and dx is negative du. So we integrate, negative 2, we raise the power here to 3 halves. So we multiply by 2/3, which gives us negative 4/3 u to the 3 halves plus c. That means we can go back to what we have in blue here, and this definite integral is going to be negative 4/3 u to the 3 halves evaluated from 0 to 12, where instead of u we have 12 minus x. To evaluate that, I'm going to need negative 4/3. 12 minus 12 is 0 to the 3 halves. And then we do the same thing with 0, so negative 4/3 times 12 minus 0 is 12 to the 3 halves. So we're left with 0 minus negative, so positive 4/3. 12 to the 3 halves would be 12 square root of 12, which is 16 times 2 root 3, and that's 32 square root of 3. Right? That'd be the entire process of calculating that exact area. Notice how we had to use u substitution in order to get it done. But let's see how all this all works out if we took a look at the region horizontally, meaning we use a horizontal representative rectangle like this. Now, since we're looking at things horizontally, it's the vertical side that is going to be a vertical change, so the change in y, which means when we want to find the width of our rectangle, we just need the functional value in terms of y, which is how our function was given to us, 12 minus y squared. There's no need to rearrange variables or do any sort of conversion like that. We can just jump right into creating our integral, which would be 12 minus y squared. And now, instead of dx, it's going to be dy. The next thing is to find out where our limits of integration are going to be. Now remember, we're looking at this region horizontally, which means we're stacking a bunch of horizontal rectangles like this, which means our interval is actually going from here to here, those two y-intercepts. Now, when we have f of y equals 12 minus y squared, those intercepts are going to be the spots where the x is equal to 0. So 12 is y squared, and each of those would be plus or minus root 12. So on top is the positive root 12, on the bottom is the negative root 12. And those would be our limits of integration then, from negative root 12 to positive root 12. Now we have our definite integral all ready to evaluate. And since it's a polynomial, it's a lot easier to integrate. So we'll end up with 12y minus 1/3 y to the third, evaluated from negative root 12 up to positive root 12, which means we plug in the positive one first and then subtract the negative one. So 12 times the positive root 12 minus 1/3 times the root 12 cubed, which would be 12 root 12. Then we're going to subtract the negative one. So negative 12 root 12 minus 1/3 times negative 12 root 12, which is 12 root 12 minus 1/3 of 12 is 4 root 12 minus negative 12 root 12 minus negative 1/3 of negative 12 would be a positive 4 root 12. So 12 and the 12 is 24, and then minus 4 would be minus 8. So we're looking at 16 root 12, and that root 12 is really 2 root 3. So we're all the way down to the same answer of 32 root 3. But a lot less complicated because we didn't have to rearrange the function and rewrite it in terms of x. We didn't have to use substitution in order to integrate. It was all very much more straightforward when we looked at that region horizontally. Here's another region that's better looked at horizontally. And let's see why by taking a look at it like we normally would vertically. And what we should notice is that it's not the same all the way across, that when we set up our representative rectangles, we have one that looks like this. Since our base is a horizontal distance, that would be delta x, and we need the vertical distance here written in terms of x, which isn't going to be too bad. We already have one of our equations written in terms of x, but as for the other one, with a little bit of algebra, adding the y squared to both sides, subtracting the x, and then taking the square root, we get the curve, the parabola, to be plus or minus the square root of 3 minus x. So the height of our representative rectangle is going to be big curve minus little curve, and in this case the big curve is x minus 1. And we subtract off the little curve, which since we are on the bottom of this would be negative square root 3 minus x, which simplifies down to x minus 1 plus square root 3 minus x. Now that representative rectangle only goes so far. It will only be the case that the line is above the parabola up until x is equal to 2. After that, we have a different rectangle. For this representative rectangle, our base is still a change in x, but now our side length right here, when we go big curve minus little curve, those are both parts of the parabola, which means the bigger curve is the positive square root, and then we'll subtract off the smaller curve, which is the negative square root. So we're looking at 2 square root 3 minus x. Now we're ready to set everything up to find that exact area. To do that, we have two separate regions, so we're going to need two separate integrals. The first one is our green representative rectangle, so x minus 1 plus square root of 3 minus x dx. And that goes from x being negative 1 up to x being 2. Then the next integral goes from x being 2 all the way out to the vertex of the parabola at 3 of 2 square root 3 minus x dx. Now, when you look at this expression, do you really want to do that? I mean, we have to do some u substitution, do it in both integrals. This thing is going to get pretty long and involved. But let's check out what it looks like when we view that region as being a horizontal region. When we look at things horizontally over the entire interval, first of all, our interval now goes from here to here. So our point on the bottom is at negative 2, and the one at the top is positive 1. Our vertical side is a vertical change, so that would be delta y, which means we're going to need our horizontal side, our base, to be written in terms of y. But over this entire interval, notice that the parabola is the bigger curve and the line is a smaller curve. So when we do big curve minus small curve, we're going to take the bigger curve written in terms of y, which it already is, so 3 minus y squared, then subtract off the smaller curve, the line, written in terms of y. Now right now the line is y equals x minus 1, so it's written in terms of x. But it's not that difficult to just add 1 to both sides and call that y plus 1. So we'll subtract off y plus 1. So this whole thing will simplify down to negative y squared minus y plus 2. And we're ready to start writing our integral. The exact area is going to be that definite integral of negative y squared minus y plus 2 dy, with a y value going from negative 2 up to positive 1. Integrating a polynomial isn't too rough. We'll have negative 1/3 y to the third minus 1/2 y squared plus 2y, evaluated from negative 2 to 1. So we plug in 1. We'll have negative 1/3 minus 1/2 plus 2. Then we plug in negative 2, so negative 2 cubed is negative 8, times negative 1/3 is 8/3. Negative 2 squared is 4, times negative 1/2 is negative 2. And 2 times negative 2 is negative 4. That'll leave us with negative 5/6 plus 2 minus 8/3 minus negative 6. And that would be 8. Getting common denominators, looks like I got negative 5/6 minus 16/6. So 8 minus 21/6 is 7/2. So 8 minus 7/2. Well, 8 minus 7/2 would be 16 minus 16/2 minus 7/2, or 9/2. Okay. And then doing it that way, I mean, notice that the integral was a lot easier to do. The hardest part of it was maybe dealing with the fractions. That was about it.